Okay, last time we talked about the equilibrium constant, which is represented by what letter? Equilibrium constant is K. Yep, capital K. And I make an expression with the equilibrium constant and to solve for the equilibrium constant. And that expression is a fraction. Which sets of my chemicals go on the numerator side? Which of them? The reactants or the products? Okay, so this is products go here and reactants go here. And there's something else even a little bit more specific that goes into that value. If I had a reaction that was 4A plus 2B yields 4C plus 3D, my K expression, my equilibrium expression would look like what? C to the fourth times D to the third over A to the fourth and B squared. Very good. Okay, so the coefficient becomes an exponent when we plug in to solve for K. Okay, that equilibrium constant is a value that's constant based on what? Okay, that wasn't a very good question. Temperature, good. Okay, you know where I was going. So temperature is what causes a change in K. These concentrations in the expression could change. But if the temperature changes, that's where we will see a difference in K. All right, so concentrations can be anything, and our K value would still come out equal to another K value with that same temperature, okay, for that reaction. Okay, we feel comfortable about that, right? When we see brackets around our compounds like that, what does that mean? Concentration. And we measure concentration in molarity, right? Capital M. Sometimes your book draws it out and says this many moles of a substance is put in this many liters, right? It makes you calculate the molarity first, right? It makes you calculate the molarity first. Sometimes it's in a 1 liter container, which makes it really easy, but sometimes you actually have to calculate that molarity before it can go into your equilibrium expression, okay? So let's go ahead and start looking at today. We are also going to be able to look at equilibrium expressions in terms of pressure, not just concentration. So we're going to look at equilibrium expressions involving pressure. If you see just a K, that would mean that we're looking at how concentrations affect equilibrium. But if you see Kp, that means we're going to look at how pressures can affect our equilibrium. Okay, tell me, what's the unit for pressure? Atmospheres. Good. Atmospheres. Okay, they did a lot of, not a lot, but a little derivation underneath there that said PV equals nRT, which is what gas law? The ideal gas law. Thank you, Bethany. Nice and fresh from physics. Okay, PV equals nRT is the ideal gas law. They put, rearranged and solved for pressure, right? They moved volume over. And then they took moles divided by volume and gave you concentration, right? So they're saying that pressure is equal to the concentration times R times delta T. And so we're going to look at that here in just a second as how we can connect K and Kp. All right, but we can solve for Kp using the same exact formula we used to solve for K, right? A to the A power, B to the B power, or whatever it was, right? We can use that same formula, this formula right here. Okay, I'm making up the compounds, but you know what I mean? This formula that we've used. This is called the law of equal mass. That's what it's called, I think. The law of something mass. Equal is what stays in my brain right now, but I think it's something like this. The law of equal mass. And we use that formula a couple different times. One with concentration to solve for K, and then now we can use it with pressures to solve for Kp. So this next slide has us setting up this example with Kp. All right, we want our pressures in atmospheres, but we set up the pressure of NH3, which is our product. And why are we squaring there? Because the coefficient is a 2. Okay, and then on the denominator side, we have P pressure. That's what that means. Pressure of H2 to the third and pressure of N2 just to the first power. Okay. So let's go ahead and plug in those values and see what we get. Okay, we're going to ignore the answer down there, but I'm going to solve for Kp using these values. pressure of NH3. And I just hate scientific notation, like, so much. But they put almost everything into scientific notation. So I'm going to just pull them out of scientific notation if I can. Like 0.89, seriously, does that need to be in scientific notation? Nope. It's so silly. I know it's sig figs, blah, blah, who cares, you know? Okay. So be really careful with our order of operations and stuff here. We want to do that exponent first. And I got a value that's pretty large.
3.9 times 10 to the 3.
Yep. Okay. I kept mine a little more exact. Why do you think they rounded that value to that answer? Yeah, sig fig. See, because I started with 2. I need to end with 2, technically. Right? I'm not going to be a stickler upon that. But almost all these questions I took directly from your book. And, you know, they follow the rules. So, okay. Any questions with how we plug that in? Are we good with that formula? Setting that up? Okay. What's the unit for K? No unit. It doesn't have one. Okay, it doesn't have one. And Kp doesn't have one either. So neither of these equilibrium constants have a unit. Okay? Good to go. All right, so let's try this one. This is a new chemical reaction, and we want to solve for Kp. We need to make sure our units have our units for pressure here are consistent. So if one of them was for some reason listed in kilopascals or something else, we would need to make sure that they're consistent at least. All right, so Kp 1.2, and this is going to be squared over 0.05 squared times 0.3 to the first power. That's about what I had, 1,920. Okay. All right. So now we're going to look at how can we connect K and Kp. Okay, so they walk through the derivation of these equations in our book and how we got from one to the other, but I'm going to give you just the brief or the end result, really. We can look at a relationship between K and Kp using this equation, and it's similar or related to the ideal gas law, but not exactly, right? It's a little bit different, okay? This says Kp is equal to K times R. What is R? 0.0821, right? 0.0821. And that's something we learned way back when we did gas laws, right? PV equals nRT, and R is 0.0821. And again, this says 0.206, but I just like it to be 21. All right, T is going to be our temperature. It does have to be in Kelvin. All right, we have to have that in Kelvin because, again, if we were 0 degrees Celsius, that would throw off all of our math, right? We got to have it in Kelvin. The only thing that's different here is that this formula is to the delta N power. And delta N is the sum of the coefficients of gaseous products minus coefficients of reactants. Okay, so let's read that again. Delta N is the sum, okay, or the change in, the sum of the product coefficients minus the sum of the reactant coefficients. But it only takes account if they're gases. So not solid or liquid, just the ones that are gas. And that's really how this whole chapter goes. If it's a solid, a liquid, or aqueous, you just get to pretty much ignore it, right? It doesn't go into the K equation, doesn't do anything. Gas is really the only thing that we're focused on in this one. Okay? So product coefficients minus reactant coefficients.
Teachers, please.
Using the value of Kp from the previous example, calculate the value of K at 35 degrees Celsius. So we're going to connect these two things. All right, we said Kp is equal to K times RT to the delta N power. So Kp from the last example, we can round it if we want and just put it at 3.9 times 10 to the fourth equals K. That's what I'm solving for. R is that. Temperature needs to be in Kelvin, so we're going to add 273 to that. And I left off one thing. I think that needs to be in parentheses. Okay, and so that's what is to the N power. Sorry, Evan, was that your question? Yes, I think I accidentally left that off when I rewrote it, but yeah, previous slide has RT in parentheses, and so that's the number that needs to be to the delta N power. So I'm going to put bigger parentheses here. 273 plus 35 is 308. And so I'm going to do that multiplication
Teacher,
first.
sorry for the interruption, but would Ryan Mullins please come to the...
And then my power on that is going to be product coefficients, right? They're all gases. So product coefficients minus reactant coefficient. So it's going to be to the negative 2 power. Okay? So all of that's going to be to the negative 2 power. 0.0821 times 308. And I'm going to put that to the negative 2 power. And when I do that, I get K times 0.00156. Is that what you had? 3.9 times 10 to the 4th. Okay, so then I'm going to divide that over. I'm going to get a huge number, right? Yeah. Okay. Oh, shoot. Um, 2.49 times 10 to the 7th. Right, since this is K, we don't put units with that. At equilibria, there's two kind of types of that. Homogeneous equilibria. What's homogeneous mean? The same throughout, right? So homogeneous equilibrium would mean that we have equilibrium of objects that are all in the same state, right? All in the same phase. The second example listed here, they're all aqueous, and the first example, they're all gaseous or vapor state. So they are considered homogeneous equilibrium. Heterogeneous equilibrium means that you have an equilibrium system that involves more than one state of matter. So something could be gas, something could be liquid, something could be solid, whatever it might be. Okay, the position of a heterogeneous equilibrium does not depend on the amount of solids or liquids present. The concentration of solids and liquids are constant. So when we look at the equilibrium expression and the equilibrium constants, we mentioned this once, but only gases go into my equilibrium expressions. So solving for K or Kp, we only use, in this case, one item. Right, we only use O2 because the other two substances here, let me go back. The other two substances are not gases. They are liquid and solid. So when I set up K, it's a product, so it goes in the numerator. It's a concentration of O2 to the third power, and that's it. Right, so the only thing that goes into those expression is gases. Okay. That's really all that section of the chapter kind of reiterates. Okay. All right. A very small a value of K that's much larger than 1 means that the equilibrium of the reaction system will consist mostly of product, which means essentially the reaction goes to completion. So if you have a K value that's really, really large, that tells you the concentration of the products is much higher than the concentration of the reactants. Would we agree with that? Right? So if we set up our equation for K, we know that K is equal to products over reactants, right? And if my numerator is significantly larger than my denominator, right, I'm going to end up with a big number. Mathematically, we see how that breaks down. It makes sense, right? So if the concentration of my products is significantly greater than the concentration of my reactants, that would mean that my equilibrium lies really far to the right, right? That my reaction almost goes to completion before it reaches equilibrium. I've produced a lot of products, right? And that's like, if I was in industry, right, if I was trying to create something or produce something, that's where I would want my equilibrium to lie, is really far to the right. I want an efficient reaction that will produce as much product as I can. Okay, the other side of that says a very small K value means that the system mostly is comprised of reactants and that this equilibrium lies to the left. So the reaction does not occur to any significant extent. So the smaller the K value, that means the less the reaction actually runs. Okay, it will stay on the reactant side. Okay. All right, we're going to move into something called the reaction quotient, and this is given with a capital Q. Reaction quotient is capital Q. When reactants and products are mixed, it's useful to know if the system is at equilibrium, and if not, where the position lies. So that's kind of what we've been looking at when we solved for K. Okay, K helps us do that. But if the concentration of one of the products or the reactants is 0, the reaction will automatically shift in the direction that produces the missing component. So if my reaction starts out with only reactants, what's the only way it can go? To the right or to the left? To the right, right? It has to start producing products before it can reach equilibrium, right? If I start with only reactants, it has to go to the right and produce products. Vice versa, if I only put in the product of my chemical reaction, it would have to go to the left, right, and produce those things until it can start to balance itself and reach an equilibrium. But this says when none of the initial concentrations are equal to 0, it's difficult to tell the equilibrium position. So this reaction quotient, this Q, is what we're going to use if none of our initial concentrations are 0, right? If we start with all 4 of our components, right? Reactant, reactant, product, product. If we put all of those into mix to start our reaction, how can we go about that? Okay? So we use and find Q when none of the initial concentrations are 0. We apply the law of mass action. Okay, that's the K equals A to the A, B to the B, right? Whatever that is, that's that equation, that formula. But when we're solving it, we use the initial concentrations instead of the equilibrium concentration. So when I'm solving for Q, I would write it out like this. And let me give you just a full example. So let's write out A to the A coefficient plus B yields C plus D. Okay, let's write out a reaction that looks like that. If I was going to solve for Q, I would do C initial, okay, and they put a little 0 here to indicate initial. Concentration of C initial to the C power times the concentration of D initial to the D power. Concentration of A initial to the A power, B initial to the B power. Okay, that's no different than solving for K, except when we do K, we use the equilibrium concentrations. And for Q, we're using the initial concentrations. That's really the difference. Okay, and then it's going to allow us to compare Q to K, and that's really the next slide here. Okay, are we doing okay? Okay, so let's go back and just review real quick. We have Q equal to K means we're at equilibrium. Q is greater to K means we need to shift left, and Q is less than K and needs to shift to the right. Okay, but let's go ahead and look at our system here. These right here, the little zeros, tell us that these are initial concentrations. And so that means we're going to solve for Q using those. Okay, so that means I'm going to look for NH3 to go in my numerator, 0.001 to the what power? Second, right here, second power. And then N2 is going to be to the first power, 0.00001. And then my H2 is going to be 0.002. And it is to the third power. I got a lot. Like that. 12.5 million maybe? I don't know. Is that the same as what you had? Okay, so our Q value came out huge, huge, huge. It was greater than K, and we need to shift left. Okay, try this one on your own. This is the same system, except we've got different initial concentrations. So you're going to solve for Q and compare. Okay, just a different set of initial concentrations here. So try this one on your own. Did we get our Q value and our K value equal to each other in this one? Yep. So if Q equals K, then that means our system must be at equilibrium already, right? We don't need a shift. It's already at equilibrium. Okay. All right, I want to try one last one here today, and that's where we're going to stop. Do you feel pretty comfortable using these formulas? Yeah. Yeah? Okay. Yeah, we need to feel comfortable for it, especially before we get to tomorrow's math that goes with it. But all right, this one says, consider an experiment in which dinitrogen tetroxide was placed in a flask and allowed to reach equilibrium at a temp where Kp equals 0.133. So Kp is what we're looking at here. We don't have a relationship between Kp and Q, so we won't look at any connection there. Kp equals 0.133. At equilibrium, the pressure of N2O4 is 2.71 atmospheres. Find the equilibrium pressure of NO2. So any thoughts about how we can go through this? Yep, it's exactly right. We're just going to still set up NO2 to the second power over N2O4, right? But here's the difference. This time we know Kp and we know this guy. So we're just really going to work backwards and do algebra to solve for NO2, right? Pretty simple. So we're going to go 0.133 equals NO2. And that NO2 is going to be squared, right? Because of our 2 coefficient. And the concentration of N2O4 is 2.71. So what's my algebra I'm going to do to get that by itself? I need to get this out of here first. So I'm going to multiply by 2.71 first. And I get about 0.360 equals NO2, concentration of NO2 squared. And you're right, that's the point where I'm going to square root. And I need to do that to both sides. And so I get a pressure, PNO2, equal to 0.6 atmospheres. That's where we're going to stop for today.